Hello students. So this is the video about the finite element method formulation of a problem with a governing equation, okay, differential equation. So we'll talk about the solution procedure, okay, of a governing equation, right? Governing differential equation. I mean, governing differential equation means that for suppose for I can say a problem with a beam problem, okay, where let's say this is a cantilever beam where we have a load acting upon this thing, okay, so there will be bending in this case. So the governing differential equation in this case is d square by dx square equal to m by ei. So this is the differential equation. So where y is the deflection, m is the bending moment, e is your modulus of elasticity, I is your moment of inertia, okay. So and this axis is y, this direction is x, this is x, this is y. So okay, I mean x will be in that direction actually, of course. So all right, here any differential equation, okay, the solution of this equation, let's consider this equation itself, here d square by dx square equal to m by ei. Solution will be finding y, okay, y. So anything d cube, some let's say d cube y by dx cube equal to something, let's say f or something, okay. So these kind of equations you have to find y, okay, y in terms of x here, because y is varying with respect to x. So anything, let's say twice x plus 3y y not y, twice x plus 3, okay, something like that, or 3 into suppose x cube plus whatever, but in terms of x, this is the solution, okay. So here we'll talk about using finite element method, okay, that is FEM, to find out the solution of a differential equation. So we will actually talk about, in your lecture we'll talk about something called weighted residual method, okay, residual method, all right, okay. So first actually we'll talk about only the domain, we'll talk about the residual first, okay, and then we'll talk about the weighted residual at the later on, okay. So anything for any differential equation, let's say we have a differential equation of the form let's say like this, okay, suppose rho d square v by y by dx square plus mg h equal to, let's say p, okay, p is the, let's say something, anything, pressure or something, whatever. So we have a differential equation like this, okay. So residual will be something called, residual of this equation is when we take everything in left hand side, okay, mgh minus p, okay, when we just take this in left hand side or right hand side, whatever you want to take it to right hand side, but normally we take it, this thing whatever we have in the right hand side, take it into your left hand side and make this right hand side equal to 0. Then we call this part as the residual, okay, equal to 0. Now see, we will call this equation as completely satisfied for y if we find an expression for y, and if we can plug in here, then the entire equation leads to 0, it gives 0, okay. Let's say suppose we have, for this equation here we have taken this equation, putting y equal to, let's say twice x plus 1, okay, when you put it here and put all the values of rho, mg, whatever we have, then everything cancels out and it is exactly equal to 0. That means this is the exact solution, okay. But in FEM is a tool to find out approximate solution, even it's a numerical method, right? So approximate solutions will be there. So that's why what we have to do is we have to actually try some functions, trial functions, okay, some expressions you have to try and put here in place of y, and we want to make this whole thing equal to 0. If we can succeed making this whole thing equal to 0, that means that is the exact solution we are talking about. Okay, but since it is not possible, okay, so that is, sometimes it may be possible, cannot say that it's not possible, but it is normally very much hard to find out. Okay, so all right, so okay, so next is, yeah, so here you see what we do is we actually try some functions of some expressions of y here, and since we cannot make it's very difficult to make this 0, we want to minimize it, or we want to make it as close as possible to 0. Okay, this thing, it is called minimizing. That's why since after putting some expression of y into this equation, we do not have a 0 value, but we have a very small non-zero value. Okay, so that is where we have the error. Okay, isn't it? That is error, because we are not making it 0. It has supposed to be 0, but it is not 0. That's why that's an error. Okay, and that is actually called here as residual. Okay, that means by putting some value of y, we have something left over. That's why this is a residual. This part is actually residual, and we have to make the residual, we have to minimize the residual minimum. Okay, so at some point, if we can make the residual 0, then we have completely succeeded. we have found the exact solution. But for many problem, it is we find the approximate solution, so we just minimize the residual. So that is the meaning of residual. Okay, now let's look at the process to find out this thing. Yeah, to find a formulation of FEM, okay, for a differential equation. So first step, you have to guess a trial solution. Okay, so we have to, let's say for 1D problem where we have only one variable here, in this case x. Okay, so we may choose any trial function. This is y only. Okay, let's say d square f of x by dx. Okay, so that means it is not a partial differential equation, 1D problem here. So the dependent variable is only dependent upon one independent variable. So that's why this is a ordinary differential equation, and we have taken any trial solution like this. That means we have taken x to the power 0, and it will have some coefficient c0. This c0 may be a number. Okay, maybe some combination of numbers also. Okay, but that there is a constant. This may be 0 later on, but we have to take it first. Okay, so c0 into x to the power 0 plus c1 into x to the power 1 plus c2 into x to the power 2, like that. Okay, so x to the power 0 is 1 only, so c0 plus c1x plus c2x, like that. The higher terms we take, the closer we go to the solution. Okay, so it's up to you. We take something like this as a trial function. Okay, we will talk about it later, when how to select a trial function. Next, we plug in this thing. Okay, and there are some boundary conditions in the differential equation. Okay, so when we plug in this, and using the boundary conditions, we try to find out these constants. Okay, that actually it is written in step 3. Here you see, assumed solution will not satisfy the differential equation completely. Okay, so because this is not, someone may assume up to this one. Okay, this term, someone may assume up to this term. Okay, so that depending upon the problem. So that when we plug it in the differential equations, may not actually, will not actually, it should be may not satisfy. So there will be some error in this case. So errors are called domain residual. Okay, and two type of residual: domain residual, boundary residual. Okay, so domain residual is when, let's say from here to here, this is the length for the beam, let's say for this one. So domain residual is when we take the entire you can say from starting point to ending point, the entire region we consider here. The residual for entire region, the differential equation for this entire region, we take in the residual form. When we take it, it's called domain residual. And the boundary residual, when we take the values at the boundaries. Okay, normally boundary conditions, that means what the value of that variable, dependent variable, at the boundaries are known. Okay, because we can find it out, right? So that's why boundary residual is normally, you can say, that can be used, I mean the sorry, and the boundary conditions can be used at that in the domain residual form. Okay, so we'll actually look into that all these things when we illustrate a problem. Then we have to find out the constants C0, C1, C2, and then assume trial in the trial solution, and we find them in such a way that the residuals can be made as low as possible. Okay, that means if we can make it 0, that it is very good, but if we cannot make it 0, we have to make it as low as possible, very small. Okay, let's look into the next thing. Okay, so FEM formulation. So this is for you is a study. Okay, for weighted residual form. We'll talk about weighted residual later. Okay, so popular weighted residual method is called Galerkin weighted residual, and a piecewise trial function approximation of the weak form of Galerkin weighted residual is very useful. So we'll talk about this, what is a piecewise trial function and weak form of Galerkin weighted residual. We'll talk about this later. Okay, so you see how to use that one. Actually here, write a domain residual form of, I mean residual form is when we take everything in your left hand side and take equal to right hand side equal to 0. Okay, that left hand side whole term is the domain residual, and any differential equation written in see any written with 0 in right hand side is domain residual from of the equation. So this is written here. So assume a trial solution. Okay, here it is written. So this function may not satisfy actually, and it will be an error. So determine unknown parameters C0, C1 in the assumed trial function in such a way that it will make the residual as low as possible. Okay, very simple. Okay, next, when the trial function satisfies the boundary differential equation completely, its domain and boundary residuals are identical to 0. Okay, so completely when it satisfies completely, then the residuals will be exactly 0, otherwise there will be a very minimum value of residual. Okay, now we'll understand the whole thing with the help of this problem. Okay, now see the governing equation for a fully developed steady laminar flow of a Newtonian viscous fluid. Okay, on an inclined flat surface is given by, this is the equation. Okay, differential equation where mu is coefficient of friction, v is fluid velocity, rho is the fluid density, c is acceleration due to gravity, and cos of theta, theta is your the angle. Now see, the thing is like here what we have is we have a some fluid is flowing over this surface, let's say. Okay, consider a 3D surface. So this surface, let's say. Okay, fluid is flowing here. Okay, some fluid is flowing like this in this direction. So we just make it inclined here. Okay, so obviously fluid will flow like this. Okay, because it is inclined. Okay, fine. So what will happen? So this is a laminar flow, obviously, so the turbulence is not there. So the you can say the layers which is just fluid layers which are touching this surface here, they are almost stagnant. Okay, they are actually not moving. There is a condition called no slip condition, and due to no slip condition, okay, so you can actually say that the layer which is adherent to this surface is not moving, and the uppermost layer is the moving, that is the layer which is moving at the highest rate. Okay, faster rate. So that means if you consider a cross section here, this point is not moving. This, as we go on, here it is moving with some velocity, and then it will move with some higher velocity. Then this is from some higher velocity, then if we connect them together, then we get a parabolic function. Okay, a parabolic curve. So this is the parabolic form, okay, of your laminar flow. Okay, now this is the high velocity v now depends upon x is this direction. See, v is a function of x, because see, when x is 0 here, then v is 0, because there is no slip condition, right? And it is actually given. So I'm sorry, this is the coordinate here. Okay, not this one. X start from this point, not this point. X is when x is 0. Okay, then velocity is the highest. Okay, when x is L here, when x reaches this you can say plate, when x is equal to L here, that means at this position velocity is 0, that is called no slip condition. Okay, that those things are given here. Okay, you see velocity at L is 0, that's why this is a no slip condition, and shear stress is 0 at x equal to 0 here because there is free flow. Okay, so you can say shear stress occurs between two layers. Okay, so the layer beneath this have 9.99% of the velocity here. Okay, so we actually get that when x equal to 0, the uppermost layer has no layer above it. Okay, so there is no shear. Okay, shear stress is 0, so that's why this is the dp by dx. Shear stress is 0 means what? You see, it is a Newtonian fluid, so tau equal to mu into dp by dx in this case, because x is the coordinate here, not y, otherwise we consider it as y. So this is 0, so this is 0 means mu cancels out and dp by dx is equal to 0, so this is shear stress is equal to 0. From there we have this boundary condition. Okay, fine. So here so what you have to do is, let us find the velocity distribution. Okay, let us find velocity distribution Vx using the weighted residual method. Okay, so let's see that. So what you have to do is, first step is assume a trial solution. Now look at the differential equation. Okay, so mu d square v by dx square plus rho g cos of theta. Okay, this theta is the angular inclination of this plate. Okay, this is the horizontal, this is the plate, so this angle here. Okay, this angle now equal to 0, so right hand side is already 0, so this thing is the residual, this is the residual. Okay, fine. Now look at this, this is the second order differential equation, right? Second order differential equation, that's why the trial solution should be at least it should have a quadratic term square, because see, if you have v equal to, let's say you take c naught plus c1 x, then you find dv by dx. Okay, then this is gone, so you will have c1. Okay, so if you find d square v by dx square, this is 0 itself. Okay, so that means we need to will be actually we should be able to differentiate with once again with x in there. I mean, it is not actually, there is no such rule. Okay, but you this thing will not lead to will lead to more error. Okay, or else c naught plus c1 x plus c2 x square plus c3 x cube also we can take. Okay, in this case we need up to d square, so we will have twice c2 x plus 3 something 6 c3 x square, something like this. Okay, so actually x will not be there, so 68, so we have a x term something like this. Okay, so depending upon the thing is, you have to choose such a trial function. Okay, depending upon your experience or whatever you can say trial function you choose, you try to minimize that. Actually you are free to choose any trial function. Okay, but sometimes you may not get the answer, that's why here it's better to take second order differential, differential equation. At least you take at least, I mean you can take higher value also, so at least take a quadratic term here. Okay, so we have taken the trial solutions. Now see, why v? Because v is what you have to find out. See, I told you, see v here, you have to find out v, so v depends upon x, so vx we have to assume. Okay, so let's assume this as your trial function. Okay, so we cannot just directly take c2 x square, no, we have to take other terms also. Okay, I mean that there may be those terms present, so that's why you have actually first write the whole expression, then you find the coordinate this coefficients. If the coefficients are 0, then it is not there, that is clear. But if see, if you have these values, then the expression will come like that. Now see, what you have to do is you have to actually plug in this value here, right? Okay, but you cannot just put directly, I mean you can put it, but you have to replace the whole d square v by dx square term. That's why you have to differentiate it twice. So differentiate it first, we get c1 to c2. Actually the second differentiation is showed somewhere else. So when you differentiate it again, so this is 2c2. Okay, 2c2, so this is shown here, 2c2. Okay, fine. Okay, that will be used later. So using the boundary conditions, so what are the boundary conditions given? So boundary conditions are, I'm sorry, okay, so here you see first boundary condition here is at x equal to L, v is 0. At x equal to 0, dv by dx is equal to 0. So use that thing here. So at x equal to L, okay, at x equal to first you use this dv by dx is equal to 0 at x equal to 0. So put x equal to 0 here and dv by dx is equal to 0. So this is 0 and this term is will go, so we'll have c1. So c1 is equal to 0, and when x equal to L, okay, dv by only v, that v is 0. So that means you put here 0 here, okay, 0. C naught is already C naught you have to find out, okay. C1 is already 0, okay, so put 0 and put in place of x we put L, okay, here. So from here C naught is equal to minus of C2 L square. So now we are left with only one unknown, that is only one unknown coefficient C naught, okay. So what you have to do is this C naught you replace in the original equation here. C naught is there, okay, here oh sorry, C naught you have to replace, we are left with only one unknown, the C2. So C naught minus this is minus C2 L square, so we write down that C2 minus of C2 L square, okay, plus 0 plus C2 x square, okay. So now we take it common, so C2 is only unknown, okay. So if you know this coefficient exactly, okay, we can determine them, that thing, then we get the exact solution, okay. Now you see here we have found a second different okay, we are differentiating it again and we get this thing d square v by dx square, okay. So the domain residual is, I told you, this expression itself. So we want to minimize this thing, so what we do, just put this d square v by dx square, try it, I mean this is a trial function, okay. When we get this we can plug it this here. Actually we can just put whole thing, the whole expression c naught plus c1x plus c2x, then d square by dx square, the whole thing. So we'll get only this 2c2, that is the same thing, okay. So this is the expression. Now we want to minimize this thing, that means we want to make this 0, okay, somehow. If we can make this 0, so that is then our problem is solved. So minimize the domain residual here. So rd is a domain residual, we want to make this 0, so just put that equal to 0. So what value of c2 makes this whole thing 0? So equal to 0, so c2 is minus of rho g cos theta divided by 2 mu, okay. This thing makes the residual 0. So this is what we need finally. So put this thing in the expression, vx is equal to c2 into x square minus l square. Here we had the expression, and only unknown was c2, okay. Now we put this and we get vx is equal to rho g cos theta divided by 2 mu into l square minus x square. So this is what we get the final expression. Now if you use this thing, okay, if you plug it this in your equation here, and you will get the entire equation as 0, okay. So this is your solution of the problem, okay. So yeah, l square minus at any x you get the velocity now, okay, understood. So therefore the above solution, now see, at x equal to L, what happens? The velocity is 0, right? The boundary condition is satisfied, so the boundary residual is also satisfied. So in this case, when x equal to 0, this is rho g cos theta L square divided by 2 mu, okay. So that is the highest value of velocity at the when x equal to 0, starting point. So at the top, topmost surface. Okay, so therefore the above solution obtained using trial function with domain residual readily verifies that it matches with exact solution. So for this problem we have found an exact solution of this. This is actually when you solve analytically to your differential equation, you will get the same expression. Okay, these type of expressions. Okay, so by putting the boundary conditions, when you solve it, I will get this expression. So this is just to show, this is an illustration of the a problem where how to take a trial function. We have shown how to take a trial function here. Okay, and how to use the how to minimize the residual here. Okay, so this is the way of this is called your weighted residual method. Okay, so actually this is the minimizing residual method. So we'll talk about another problem. Okay, similar type of problem, and then we'll talk about the weighted residual. Okay, now actually weighted residual means we have to multiply something with the residual. Okay, so here you see, consider a uniform rod subjected to a uniform axial, actually only one axial is axial load, as illustrated in the figure. Okay, following figure. So we have a beam here. Okay, actually this is under axial loading, this is not a beam. Okay, so if we suppose had we been applying the this vertical load, okay, then this will be a your beam, otherwise it is, we'll call this as a rod. Okay, so it is being pulled by some load q0. Okay, so here we have the length. Okay, so the governing equation in this case is ae d square u by dx square plus q0 equal to 0 with boundary conditions. Now see what will be the boundary condition. U here is the variable that is dependent upon x. Okay, so u is the displacement. So what will happen to this rod when we are pulling with some force, constant force q0? Okay, so this is pulling the whole thing, right? So there will be displacement u. U is the displacement in this case. So it is not written, but u is the displacement, and u is a function of x. You see, the displacement will be more, okay, at the end, because we are pulling it at this point. Okay, so this is elastic, so this will be, the deflection will be highest at this point and lowest at this point. Okay, this boundary, this will not move at all because this is fixed. Okay, unless there is a failure, this point is fixed, so this will not move. So that's why boundary conditions are when x is equal to 0, the displacement is 0, so u0 is equal to 0. Okay, so this is the first thing. Next, at this point, okay, du by dx, this is your okay, this is given that the du by dx is equal to, at x equal to L, this is 0. Okay, so okay, so find the approximate solution of the problem in this case. Okay, so this is actually given for you, okay, in this problem. So assume a trial solution to the problem. These boundary conditions should be given to you. Okay, so assume a trial solution for a problem. This is the rate of change of your this one, since this point is the end point. Okay, so the rate of change will not will be 0. Rate at which u is changing, this I can say displacement is changing with respect to x is 0 at this point, because there is no other nothing beyond this point. Okay, that's why the rate of change is 0. Okay, at x equal to L, right? So just take assume a trial solution in this problem. Again, here you see we have d square u by dx square, so we'll take at least we'll take a trial solution of quadratic form. Okay, so this is the trial solution we have taken. Okay, we have to find out the coefficients C0, C1, C2. Okay, fine. So we have to differentiate it twice. Okay, so because since we have this term d square u by dx square here, so differentiate it once, so we will get C1 plus 2C2. Okay, so we can use now the first boundary condition, at x equal to L du by dx is equal to 0. So at x equal to L, du by dx. Actually we can use either of them. So we use the first boundary condition here first. So at x equal to 0, this u is 0. So when you put that, this whole thing is 0, c naught plus c1 0 plus c2 0 square. Here c naught is equal to 0. Okay, fine. Next is du by dx at x equal to L is equal to 0. So du by dx here is 0 when x equal to, this is L. So c1 plus 2 c2 L. Okay, so c1 here is minus of 2 c2 L. Okay, fine. So this is c1. So now we have got c1 c0. Okay, so we can just put them here. So in the trial solution, c0 is 0, c1 is minus 2 c2 L x plus c2 x square. So c2 takes, we take c2 as common. Now again we are left with only one unknown constant. So what you have to do, you have to minimize the residual now. Okay, so now once again if we differentiate, we get 2c2. So residual is this one. Okay, a d square. So the right hand side, because right hand side we have 0, left hand side the whole term is there. So this is your residual. Okay, so we have to minimize this. That means we have to make this is equal to 0. So we put d square by dx square is equal to, that is 2c2. Okay, so ae into 2c2 plus q naught is equal to 0. Okay, this is the residual. We want to make this 0. At what value of c2 this whole thing is 0? We have to find out c2 is equal to minus q naught divided by 2ae. Okay, so here we finally our solution will be when we put this c2 value here in this equation. Okay, right? So this is minus q naught 2ae, okay, into x square minus 2 lx. We take minus sign inside, so this will be 2lx minus x square. So this is q naught by 2ae into 2xl minus x square. That means using this equation now, expression, at any value of x we can find out the here its extension. Okay, at any point of x. So when x equal to L, you see this is L square twice L square L square. So this is twice, this will be L square. So q naught L square divided by 2ae is the maximum amount of extension at this point at the end. And when x equal to 0, you see this whole thing is 0. Okay, so it satisfies the boundary conditions also. So this is your required solution. So these are exact solutions actually. So in the next video we'll talk about the weighted residual technique. Okay, and how to use the weighted residual technique to make the residual minimum at the entire domain. See, for these two problems actually it is becoming 0 everywhere. Okay, I mean the residual we could make it 0 exactly by using this, but for some problem it may not be effective. Okay, that's why there is a technique called weighted residual. Okay, I mean we have to multiply. What we have to do is here is, see, in this case we made rd is equal to 0 and we found something, okay, that makes rd is equal to 0, but sometimes that is not possible. So what we do is we multiply some function multiplied by rd. Okay, this rd multiplied by some function. Okay, and we actually make the whole thing approximately 0 at each and every point of the domain. Okay, so this function is called weighting function. Actually it adds some weight to your residual, we call. So this is called weighting function. So multiplying this function with rd and making it 0 at the entire domain, how do we do it is we integrate it actually, and we'll look into that and integrate it over the entire length. If it is a rod, then entire length. Okay, anything, if let's say some limit is whatever a to b. Okay, so a is maybe 0 normally and b is the highest limit, this is the lower limit to higher limit. We integrate the whole thing. Okay, weighted function is written as w. Okay, w multiplied by rd integration of that is equal to 0. This is called weighted residual method. Okay, and Galerkin weighted residual method says that how to select this, how to choose the weighted function. Okay, we cannot take any weighted any function here, randomized function. We have to take a particular function to be multiplied with this residual. Okay, we'll talk about that in the next video. Thank you.